Welcome back, everyone. Okay, let's jump right into this detailed explainer covering Section 12.3 of our software engineering course. Today, we're examining the highly regulated, high-stakes world of safety-critical software. We're talking about the systems that keep airplanes in the sky, nuclear reactors stable, and life-saving medical devices functioning exactly as they should. In this environment, a software bug doesn't just mean a frozen screen or an annoying crash. It can literally mean a catastrophic failure. Because of that immense risk, the engineering processes we use are just incredibly rigorous. And that is exactly what we're going to unpack today.
So here is our agenda for this lecture. 1. Introduction to safety processes. 2. Core safety assurance activities. 3. Mathematical proof, which is formal verification. 4. Automated state or model checking. 5. Scanning code through static analysis. And finally, 6. Our lecture summary and exam focus. Let's start with Section 1, Introduction to Safety Processes.
We really need to begin by completely shattering the assumption that building a safety-critical system is just like building, say, a standard mobile app or a web platform. The context is entirely different. Now, you might be wondering about popular methodologies like Agile development. Agile is fantastic for embracing change and keeping heavy documentation to a minimum, but it genuinely struggles in safety-critical domains. Why? Well, because these systems are heavily regulated by external government bodies. Regulators don't just want to see working code. They demand extensive, unbroken trails of documentation and absolute proof that a system is safe before it is ever allowed to be deployed. They need a highly structured, plan-based approach with checks at every single stage. So, to sum it up, standard Agile simply cannot provide the rigorous documented proof required by law without undergoing some major modifications.
Moving on to Section 2, Core Safety Assurance Activities.
Before we get into the really complex mathematics, we need to understand the foundational, human-led processes that form the absolute bedrock of safety engineering. Let's start with a crucial definition. What exactly is safety assurance? Think of it as a set of activities running parallel to the standard software development process to absolutely guarantee that a system will operate safely. It's kind of like a shadow process. While your developers are busy writing code and building features, your safety assurance team is constantly running alongside them, checking, verifying, and constantly asking, wait, could this feature cause harm? And these activities must be thoroughly documented, because this documentation forms the very evidence that gets handed over to regulators.
And where is all this documented? It all goes into the hazard register. Now, this is absolutely critical. This isn't just a basic spreadsheet. It is the central legal document of a project. It tracks every single potential hazard identified during the project, details exactly how the engineering team mitigated that hazard, and crucially records exactly who signed off on it. Personal accountability is the whole game here. If an accident actually happens, investigators will immediately look at the hazard register to see who was responsible for ensuring safety. Engineers must legally stand by their decisions. Driven by that hazard register, teams will regularly conduct safety reviews. These are meticulous, human-led inspections where engineers are specifically hunting for underlying assumptions that could cause accidents. They aren't just looking for broken code, right? They're looking for dangerous logic. For example, let's say a team assumes an aircraft is safely on the ground merely because the wheels are spinning. Well, a safety review has to challenge that assumption. What if the plane is just hydroplaning on a wet runway? These reviews exist to catch dangerous human oversights before they become fatal errors. Finally, in our human-led processes, we have safety certification. Often, a development team will buy an off-the-shelf software component to save time. Makes sense, right? But in a safety-critical system, you absolutely cannot blindly trust external code. Safety certification is the process where an entirely independent external team verifies and certifies that this external software is genuinely safe before it is ever allowed to be plugged into the critical system. To quickly recap, our core human-led activities revolve around tracking accountability in the hazard register, catching bad assumptions through safety reviews, and verifying external code via safety certification. Let's look at Section 3, Mathematical Proof, also known as formal verification. Now that we understand the human and legal elements, let's shift gears to the mathematical and automated technical processes used to guarantee safety. To understand formal verification, we have to accept a somewhat harsh truth of software engineering. Testing can never find every single bug. Testing only shows the presence of errors, not their absence. So, for the absolute highest level of safety, we turn to formal verification. This is the process of using rigorous mathematics to absolutely prove that the software code perfectly matches the system specification.
You aren't just running a bunch of test cases hoping to catch an error. You are creating an ironclad mathematical proof that the program will always behave correctly. Let's step through the practical realities of this approach. First off, it is an extremely expensive and intellectually difficult process. You need specialized mathematicians and highly trained software engineers. Second, despite that high cost, it is highly valued in industries like aerospace. Companies like Airbus use formal verification routinely because, in the long run, proving a core component mathematically can actually save them money by completely removing the need for exhaustive traditional unit testing. But third, and this is absolutely vital, we must highlight a fatal drawback. A mathematical proof is entirely useless if the original specification is wrong. If the engineers told the mathematicians to prove the wrong behavior, the system will just execute that wrong behavior perfectly. So, formal verification offers absolute mathematical proof of safety and reduces testing, but it's expensive and totally reliant on flawless initial specifications.
Moving to Section 4, Automated State Model Checking. Let's see how this builds into our next topic. We're going to look at a specific, highly automated type of formal analysis called model checking. It's a truly brilliant technique. Basically, we define it as building a state model of the system and then using a powerful software tool to automatically explore every single possible path through that model to ensure it never ever enters a dangerous state. So instead of humans manually doing the math, we use immense computing power to simulate every possible sequence of events your program could ever experience, just verifying that a catastrophic state is totally impossible to reach. Let's walk through the exact workflow of how model checking actually operates. We start right at the beginning with requirements or the actual program itself. This immediately splits into two distinct tasks. On one side, we have model building, where we translate the software into an extended finite state model of the system. On the other side, we handle property specification, where we define the desired system properties. For example, setting a hard rule that the system must never open a pressure valve when the pressure is critically high. Both that model and the desired properties are then fed straight into the model checker software tool. The tool exhaustively analyzing the model. Finally, it outputs either a confirmation that the system is perfectly safe or a counterexample. And that counterexample is incredibly useful because it shows the engineers the exact sequence of events that leads to a dangerous state, so they know exactly what to fix. A huge benefit of model checking is that it is absolutely fantastic for analyzing concurrent systems. Concurrent systems where multiple processes are running at the exact same time are notoriously difficult to test normally because bugs often depend on exact microsecond timing. Well, model checking explores all those interleaved, time-sensitive transitions flawlessly. However, the catch is that because it explores every single path, as the system grows, the number of paths literally explodes. Therefore, it requires massive computational power to run exhaustively. It's usually way too expensive to run on an entire massive application, so it's typically reserved for the most critical core components. So, summary time. Model checking automatically simulates every possible state to guarantee safety, especially in complex concurrent systems, but demands massive computing power.
Section 5, Scanning Code, Static Analysis. So we've seen how expensive and heavy formal verification and model checking can be, so what is the everyday tool that engineers actually use? That brings us to our final technical process. Let's define it clearly. Static program analysis involves using automated software tools that scan the raw source code text without executing it to find anomalies. Notice the contrast here. Testing requires running the code. Model checking requires building a complex state model. Static analysis is basically like a highly advanced spell checker for your code. It just reads the raw text of the program, looking for patterns that are known to cause bugs. Let's break down exactly what these analyzers are looking for. They're great at spotting different fault classes. Take data faults, for example. A static analyzer can instantly spot if you have variables being used before initialization or variables declared but never actually used. When it comes to control faults, it can scan the text and flag unreachable code, code that the program could never logically execute. It can also find storage management faults like sneaky memory leaks. It finds all these vulnerabilities in seconds, purely by reading the syntax and structure of the code. The practical realities of static analysis are exactly why it is so insanely popular. It is incredibly cheap and fast compared to formal methods. Seriously, you can run it on your laptop right now. It acts as a brilliant first line of defense, detecting common vulnerabilities super quickly. But there is a major drawback you absolutely must remember. It often generates highly annoying false positives.
Because it is just scanning for patterns, it might flag a perfectly safe piece of code as dangerous. Engineers then have to spend valuable time manually filtering out these false alarms. To wrap this up, static analysis is a fast, cheap way to scan code text for common vulnerabilities, though it definitely requires engineers to manually manage those false positives.
And finally, Section 6, Lecture Summary and Exam Focus.
Okay, we have covered a ton of ground today, moving all the way from human regulation to mathematical models and code scanners. Let's enter our final review, and I'm explicitly highlighting the key facts that are highly likely to pop up in your exams. First, I practically guarantee you will be asked to compare model checking with static program analysis. You really must understand the exact differences. Model checking involves exploring exhaustive state paths, requires massive computational power, and is the absolute best choice for complex concurrent systems. On the flip side, static program analysis simply scans the raw source text of the code without running it. It is very cheap and fast, but its main flaw is that it generates frustrating false positives. Make sure you understand this contrast perfectly. Here are a few other crucial exam points. You must understand why Agile methodologies struggle so much in safety-critical environments. It's due to that lack of rigorous upfront documentation required by regulators. You also need to know what a hazard register is. Remember, it is not just a to-do list. It is the central legal document for personal accountability. And finally, remember the absolute Achilles heel of formal verification. It relies entirely on correct starting specifications. If those are wrong, you are just flawlessly proving the wrong behavior. I want to wrap up this explainer with a really powerful concluding thought to contextualize everything we've talked about today. While formal methods and model checking are expensive, the cost of a catastrophic failure in an airplane or nuclear reactor is infinitely higher. The processes we discussed today might seem slow, burdensome, and mathematically exhausting, but when human lives are genuinely on the line, there is absolutely no room for error. The rigorous discipline of safety engineering ensures that the technology we rely on every single day remains safe. Next time, we're going to build directly on these concepts as we transition into reliability engineering, exploring exactly how we keep these safe systems running continuously without downtime. Study these processes well, because one day the systems you build might just depend on them. Thanks for joining me on this deep dive, and I'll catch you in the next lecture.